Hello, my name is Eric Ramos Aguilar and I'm going to present the work Automatic Phonetic Segmentation of the Yuhmu language using male-scale spectral parameters. The following PhD collaborated on this work José Arturo Olvera López, Iván Olmos Pineda, and Ricardo Ramos Aguilar. This is the content of the presentation: introduction, proposal, experiments and result, and conclusion. In the introduction, one of the challenges we face is dealing with languages that lack digital resources for analysis. These languages are often low-resource languages, such as indigenous language of Mexico, which do not have digital information for automatic analysis. Therefore, there is a need to generate various types of analysis, such as automatic phonetic segmentation. Automatic phonetic segmentation enables different tasks: natural language processing, aiming for computers to understand the language by using the smallest distinctive units in the phonetic plane. There are two types of phonetic segmentation: explicit and implicit. The first involves voice-to-text alignment and supervised analyzing features, whereas implicit segmentation is considered unsupervised because it does not work directly with a phonetic transcription, making it an unsupervised segmentation. This is where our problem arises, as we are working with a language that lacks textual representation and only digital audio files are available. This language is Yuhmu. Our proposal considers digital audio of words in Yuhmu as input. A male-scale spectrogram is then generated with variation in its parameters. The cosine distance is applied to the spectral matrix to obtain the similarity or contrast in the spectrum, which enhances phonetic separation. Secondly, information filtering is performed, where experimental thresholds are used to eliminate data and found zeros in the matrix. Those obtain columns that segment the spectrograms. These experiments generate different results. In the experimental stage, we use a dataset of digital audio from the Yuhmu language, a variant of Otomí spoken in Ixtenco, Tlaxcala, Mexico. This language has 32 phonemes, 12 vowels, and 20 consonants. The audio files lack a textual transcription, and their duration range from approximately 376 milliseconds to 1.118 seconds. The evaluation metric used is the segment error rate, which considers the total numbers of segment errors and the number of segments in the transcription. For the generation of a spectrum, various parameters were considered, such as window size, window type, overlap, number of triangle filters, and a threshold. The main idea was to find the best combination of the parameters to obtain the ideal segments. In this part, generate of result from the experimentation, an average share of 59.94% was obtained across all tests. However, by reducing the combination of parameters used to generate male-scale spectrograms, it was observed that the best results were achieved with a threshold of 0.4, a 75% overlap, and any numbers of filters or triangular filters. The best result was a share of 38.79%, which is comparable to the state-of-the-art words. Moreover, a more exhaustive analysis of parameters showed that certain combinations led to a 0% error rate. This is particularly rewarding because it suggests that dynamic parameters can be incorporated to find the best result, not just a single set, but for multiple combinations for a single word. In addition, the proposed methods include a visual representation of the segments. This provides both statistic and visual insights, allowing us to pinpoint where the system made errors and where it performed optimally, as well as providing visual representation of the phonetic segmentation. In the other case, the table presents a statistical analysis of the effect of three parameters of the segmentation: error rate, overlap, threshold, and MEL filter bands. Friedman and ANOVA tests were applied to compare the groups. The results indicate that only the threshold parameters show a statistically significant difference, with p-values of 0.0456 Friedman 29 pairs and 0.0026 ANOVA. In contrast, overlap p equals 0.7047 and 0.0689, and MEL filter banks p equal to 0.1718 and 0.1811 did not show significant effects under air test. In other case, K-means clustering was applied to the MEL scale spectrogram to group acoustical similar segment based on energy patterns. Within it identifies regions with similar power. It does not perform phonetic or temporal segmentation. Thus, it serves as complementary tool rather than a replacement. The number of clusters range from 2 to 8 depending on the spectrum. In conclusion, the study shows that the phoneme segmentation is essential for analysis and evaluation in indigenous languages without a formal writing system like Yuhmu. Optimal parameters were found for accurate automatic segmentation detection. Additionally, acoustic embedding enabled developed digital education models applied to the other indigenous languages like Ñatró, Totonacu, and Náhuatl. That's all. Thank you very much.